So, welcome everyone again. Today we're going to talk about, I'll show you some basic quantum algorithms, and I'll start with the Deutsche algorithm, which is like one of the easiest algorithms. For that, I will first introduce oracles and then show you the theoretical part of it, where we will do some calculations. I hope it's not going to get too math intense. And then in the second hour, we will talk about Grover's algorithm, where I will show you also the theoretical part, and then especially also talk a bit more about amplitude amplification. Good, so let's start with the Deutsche algorithm. Okay, so as I mentioned before, the first thing I need to introduce for that are what we call oracles. For an oracle, oracles are basically some assumption that we make. So we assume that we have access to something that we call an oracle, which is just some kind of physical device in which we cannot look inside, so we don't know how it works. But to which we can pass some queries. And which then return some answers. So in this case, the goal is that we want to determine some property of our oracle. Using a minimal number of queries. So first, when I heard about these oracles, I thought, okay, so quantum computing is just fancy because we have oracles and we just, instead of solving the problem, we introduce some oracles, which we then just pass the problem to, and which then solves the problem for us. Great. But no, this is actually not the case, of course. Then, of course, quantum computing wouldn't be that great. And oracles can actually also be very, very different depending on what problem we're looking at. They have different functions. So in general, it's just really just some functions that we can also efficiently program. Or in the case of Grover's algorithm, it's just some unknown function, but it's also super easy to. It's like an efficient function where we just don't know what it does, as you will see in a second. But so on a classical computer, such an oracle is given by a function in which we can put, so some function f that has an input string consisting of n bits, and that outputs a bit string with m bits in general. On a quantum computer, however, the oracle must, as all the function that we discussed yesterday, the oracle must be reversible. So we have our oracle function OF, the gate that the oracle implements. We have x, input x. X is our n qubits. Then we have m other qubits, y. And we have the oracle OF. And we output x and y plus x, y plus f of x. That way we can construct the function, any given function f, to be reversible, because, well, you've seen that yesterday when we looked at the C0 gate, and we saw that we do get the output y plus f of x. In that case, y was just 0, so that we could just get f of x as an output function. But then we also had to introduce an extra, had to output an extra output x, like the output the x again, so that the whole thing is reversible and we can construct the inputs. The same now works here, that the oracle has to be reversible, and OF is now what we call a bit oracle. This is the function that implements, this is the gate that implements our function f. And so it can be seen as a unitary, because I told you everything has to be unitary in quantum mechanics. And it performs the map OF acting on x and y, which are the inputs, and then outputs x and y plus f of x. Sorry, actually, in the function yesterday, f of x was just x, and we output y plus x as the C0 gate. Anyway, so now for any function f that takes those n input bits and maps it to just one bit, we can construct a different kind of unitary or oracle function, which we call UF. And here we basically do the same as before. We have our two inputs, x and y, but the y we choose to be very specific. It cannot just be any bit or qubit, but it's actually going to be a qubit in the minus state. So in the state 0, -1. And then we can act with the oracle OF on it. We get some output y prime and some output UF light on x. And now we consider this whole thing. Do a box around that, and this is going to be our unitary UF. Now let's see why we can do that and why this holds as, and why in the end we just apply UF on x and why we don't need to worry about our y. So if we apply OF to x and y, well, we have 1 over square root of 2 because of the superposition state of y. And then we get x and the oracle function OF. As we said, it implements, it returns x and y plus f of x. So it returns x, and for the first bit, in the first part of the superposition, it's 0, so we get 0 plus f of x. And in the second part of the superposition, we can return x, but then 1 plus f of x. And well, this we can just rewrite again as 1 over square root of 2, and now x times 0 minus 1, which equals x and y, for the case where f of x just equals 0. Because then here we just get 0, and here we just get 1. Then for the case where f of x equals, because we said f of x can be only either 0 or 1, just one bit that it returns. And then for the case where it is 1, we will get x, but then this will be 1 and this will be 0, because we just add, well, we add one bit to it. We add 1 to our bit, so we get 1 minus 0, which is minus x times y. This is for the case where f of x equals 1. So in total, we can write the what OF applied to x and y does as minus 1 to the power f of x times y. And that whole thing is actually independent of y, which is why we call this qubit y here an ancilla qubit. So UF is what we call a phase oracle, because it just adds a phase. It doesn't change our bits x and y, it just adds this phase. And the performance of the phase oracle is the map U of f times applied to x gives us minus 1 to the power f of x times x. And we'll see that actually in all the algorithms that we're gonna look at, we just need these phase oracles. Something that confused me a lot in the beginning is that this ancilla qubit, y, yes, it does get returned, like we have a y input here, and then we have the y output there, but somehow there's this phase of minus 1, which I thought belongs maybe rather to the second qubit than to the first qubit. Like, how could I say that the minus sign actually goes to the second rather than to the first? But okay, what I learned by now is this phase is something that just applies to the full state. It's nothing that we can say, okay, either the first or the second qubit is in that state. So minus the state minus x times y is the same as if I say minus x tensor y, and it's the same as if I say x tensor minus y. So this is all mathematically, it's easy to see, it's all the same. And also physically, well, according to our laws of quantum mechanics, this is really just writing the way that we write the wires, that we have like one wire per qubit, just is maybe a bit misleading in the sense that you would then assume that the minus signs or all the different phases belong to one of the qubits, but they really just belong to the overall state, and there's like overall entanglement and everything. So yeah, mathematically you can see that all works, and this, we really don't need to worry about our qubit y then, which just gets in and out in the same way. Okay, so using these phase oracles is a big thing that we need for the Deutsche algorithm, but something else that we actually need is, again, the Hadamard Gates that we looked at yesterday. However, this time on n qubits. For that, we recall that if we apply Hadamard to the state 0, we get the state plus. So we get the state 1 over square root of 2 times 0 plus 1. If, however, we apply to state 1, we'll get the minus state. So we'll get 1 over square root of 2 times 0 minus 1. So we could write it just as we did for teleportation yesterday. We can just rewrite it in a slightly more complicated way. If we assume that x is only either 0 or 1. So if we say x is just 1, is not in a superposition state, but just either 0 or 1, then the output, we can rewrite it as 1 over square root of 2 times 0 plus minus 1 to the power x times 1. Because that gives us 0 plus 1 in the case where x equals 0, and 0 minus 1 in the case where x equals 1. And let's write it even more complicated. We can also rewrite it as 1 over square root of 2 times minus 1 to the power 0 times x times the state 0 plus minus 1 to the power 1 times x to state 1. So now we just added here this thing, which is anyway plus 1. But the reason I do that is so that I can write the whole thing it makes sense to write it as a sum. But you can see that this holds. I can write it as a sum over the bit over k, which is one of the two bits 0 or 1, minus 1 to the power k times x, sum over there, cat k. This is just describing the effect of a Hadamard gate to a single qubit that is initially either in 0 or in 1. So why I'm doing this is because now I want to generalize it to n qubits. So let's say x is an n-bit string. Still only bits, so only 0 or 1, not superposition. But then I can write x as x0, x1, and so on until xn minus 1. We apply a Hadamard gate to each of them. And then we'll get the outputs y0, y1, and so on till yn minus 1, which I combine as bit string y. Or, sorry, qubits. Can be, of course, in a superposition. They are in a superposition, in fact. So, and y is just Hadamard to the power n. So this means that what I'm writing here means that I'm applying h tensor h, tensor h, and so on. So on all n qubits, I apply Hadamard gate, apply to x. And it's actually just generalized from the one that I did for 1 qubit. So it's 1 over square root of 2 to the power n, because we have, due to normalization. And now we're summing not only over k and 0 and 1, but over all n bit strings, all 2 to the n different bit strings. So k and 0, 1 to the power n means we have all the different 2 to the n bit strings. So 0, 0, 0, 0, 0, 1, and so on. And then we have minus 1 to the power k times x, as before, times k. And here k times x, this is now the inner product of the 2 bit strings k and x. It's maybe not obvious for you that this holds, but you can actually quite easily show, for example, using induction, that this follows and that this holds as well. What it means is that now, or how one could actually maybe get an intuition for that, is that we know that if every x is either 0 or 1, then we know that every yi is either in the plus state or in the minus state. So it is kind of clear if all of them are either plus or minus, that y must be a superposition of all possible bit strings. And let's just show an example with 2 bits. So maybe you get more intuition for that then. So let's assume x would be 0, 1. So we have 0 and 1 as the 2 inputs. We apply a Hadamard gate to each of them. And then the output, the output is clearly plus here and minus here. So the overall output y is actually plus tensor minus. But if we write that out, all the terms, we will get 0, 0, minus 0, 1, plus 1, 0, minus 1, 1. And this is exactly of the form of the sum that we had before. So this is 1 over square root of 2 to the power 2 times the sum over k over all 4 bit strings minus 1 to the power, and then we have here k times 0, 1. Good. Now we have all the basics that we need for understanding the Hadamard, the Deutsche algorithm. We understood what oracles are. We looked at how Hadamard Gates act on n qubits. And that's all that we need for the Deutsche Algorithm, really. So let's discuss that one. So in the Deutsche algorithm, we are given a function f that maps from 0, 1, so from an n-bit bit string to either 0 or 1, which is realized by such an oracle, as described before. And of this oracle, we know that it can be one out of two different functions. It can either be constant, where constant would mean that all inputs map to the same output. So it would always constantly return 0, or it would constantly return 1. Or it is balanced, which means that the number of inputs that map to 0 is equal to the number of inputs that map to 1. They have a half-half, 50-50 probability to get 0 or 1. And you see, this is an oracle that this is just some function that's like this kind of black box that can be implemented very easily, and that does not solve our problem, because what our problem, the goal of the algorithm is that we want to determine whether the function f is actually constant or balanced. Now, if I classically would try to solve that problem, then we would need, obviously, if I just ask the oracle once, I just give one input and I get a 1. I have no idea whether the oracle is actually constant or balanced. I need to ask it at least twice. And as soon as I get two different outputs, I know, okay, it definitely is balanced because it's clearly not constant. However, if we get twice the same output, then we would need to ask again, because then of course we still don't know whether it's constant or not. It could have happened that we just happen to get twice the same output, and it could actually also happen that we get 5 times the same output, even though it is actually balanced. And in the worst case, we need to ask it n/2 plus 1 times, because so n is the number of possible bit strings, which is 2 to the n. And so n/2 is the number of possible bit strings that even if it's constant, even if it's balanced, could return the same value. So in the worst case, I'm getting n/2 times the same, and then I do one more query, and that then tells me whether it's for sure constant or balanced. So n, as I said, is the number of input bits, and capital N, which equals 2 to the n, is the number of realizable bit strings. Maybe a demonstrative example that you could think of is if I give you a coin and I tell you this coin, and let's assume, I mean, of course, you have different ways to flip it, but assume you could somehow throw it and there would be 2 to the n different ways to throw it. And I'm asking you, is this coin fair? So either the coin would always land on the same side, or it would, like, with half of the ways that you throw it, it would actually land on one side and the other half on the other side. So if you throw it once, you don't know whether it's constant or not, but once you throw it multiple times, or more than the number of half of the different ways that you can throw it, well, then you know at some point whether it is fair or not, or just as a maybe slightly demonstrative example. Of course, that's not accurate because you have more than 2 to the n different ways to throw it. But okay, let's talk about the quantum solution. The quantum solution in any case needs only exactly one Curie. And the reason for that is that we can actually use what we discovered yesterday, the so-called superposition. So the circuit for the Deutsche algorithm is the following. We start in state 0 on in total n different qubits. We apply a Hadamard gate to each of them. Then we apply a unitary UF that implements our oracle, so the unitary that implements the oracle function, the phase oracle. Then another set of Hadamard gates. And in the end, we do a measurement of all the n qubits. And here we get a bit y0, y1, and so on until y n minus 1. This is our bit string y. And by the way, I've used that already in teleportation, but might have not explained that. If I draw 2 lines, that means that we have classical bits. That's why here we have the classical 2 lines after the measurement. So these are measurement operators, or yeah. And afterwards we have a classical bit, either 0 or 1. So let's see what happens at the different stages. So initially, this is our state psi 0. And okay, let me very quickly give you the claim. The claim, and already, is that if the outcome y, so the final outcome of n bits, classical outcome, if it equals the bit string 0, 0, and so on, n0, so the 0-bit string, and then f is constant. Otherwise, if we get any other bit string, then it is balanced. And for the proof, we just work ourselves through the different stages. So we start with the state psi 0. So psi 0 is just the bit string, the 0-bit string. So we just have, because all qubits start in 0, you can just write that as 0 to the power n. Then we apply Hadamard gates to all qubits. And well, we just learned what that means. So we have Hadamard to the power n applied to our state psi 0. We get the normalization factor of 1 over square root of 2 to the power n. And the sum over all 2 to the n bit strings, the coordinal x, minus 1 to the power x times psi 0. And then cat x. But hey, we actually know that this psi 0 is just the 0-bit string, which means that any inner product of, if I multiply it with no matter what x is, this will always give me 0 in a product. So the -1 to the power 0 is just +1. So we can just write it as sum over all states, and then here we get x. So just an equal superposition of all states without any phases. Then we have our next step, which is applying the oracle. And we get a state psi2. For the state psi2, we applied UF to state psi1. And because everything in quantum mechanics seems to be linear, so we can move that a bit. We can move the effect of the oracle into the sum. We have here the sum over all x, 0, 1 to the power n. And then here UF, that's x, because this is clearly linear. Just a matrix multiplication. And, well, what we learned is UF applied to x just gives us the phase. It's a phase oracle. So it will just give us -1 to the power f of x. So x. And we're almost done. In the last set of gates, we get to state psi3 by applying again n Hadamard Gates to the state psi2. So similar as before, we use linearity to move the Hadamard Gates. It's just a phase, so we can move the Hadamard Gates to all the way here to be applied to the state x, to the states x. We get another prefactor, so we have 1/2 to the n as normalization. We still have our sum over all x with the phases. And then we have the other sum, another sum that comes now from the new Hadamard set of Hadamard Gates. Let's write it as a sum over all k, all the bit strings, and here we have then -1 to the power k times x. Times k. And we can now just change the order of the sums a bit. So we get the sum over all k to the front. And here we have 1/2 to the power n, sum over all x, then -1 to the power f of x plus k times x, just putting the two phases together, times k. And so this I'll just define as amplitude ck, so that I can write the whole quantum state. I can write as a sum over the k 2 to the n different bit strings, so that I can give the index k with amplitude ck. Here we have the cat k. Good. So we have a superposition of just some bit strings k in the end that have amplitude ck. If you remember the Born rule, we can now determine what the probability is to measure the 0 string, which I claim tells us whether or not our oracle was constant or balanced. So the probability to measure y to be just zeros is by the Born rule given as the projection onto the 0-bit string. So the inner product of psi3 and 0, absolute value squared. So we have, and we can now put in our psi3 in here. Then we get the sum over all k. Then we have here ck times this projection. And this inner product squared. But, well, what we know is that, so k runs over all possible bit strings, over all the 2 to the n different bit strings. However, that means that if k equals the 0-bit string, the inner product is 1 by normalization, you know that. If, however, k is anything else, then it is orthogonal to the 0-bit string. So we'll get 0. So we can just write the sum. Instead of the sum, we only left with one term, which is the C 0, 0, 0, and so on term coefficient. Absolute value squared. So we just need to look at the definition of that term again. It's 1 over 2 to the n. And then the sum over all x. And we have minus 1 to the power f of x plus k times x. But again, k now is just the 0-bit string. So similar as when we applied the first Hadamard gate, here we get again, it's all 0, so we just get the factor of plus 1. And so the second term here disappears. So we're just left with minus 1 to the power f of x, and then squared. And okay, now we have 3 different cases. We have the case where f of x is constantly 0. In that case, this term here is always plus 1, so we just get plus 2 to the power n. Then we have the other case where f of x is constantly 1. In this case, we get always minus 1, so we just get minus 2 to the power n. And we have the case where f of x is balanced. In that case, half of the time it gives us 0, half of the time it gives us 1. So if we sum over all of them, then they cancel each other out and we just get 0. Which means now the probability to measure the 0-bit string is 1, because here we have the cancels of that. If f is constant, and it is 0 if f is balanced. And well, that was exactly the claim. The claim was if it equals exactly the bit string if f is constant, otherwise it is balanced. So if it is constant, we have a 1%, the probability is 1, so we have a 100% chance to definitely measure the 0-bit string. And if it's balanced, we have 0 chance to measure the bit string, but we will measure anything else. So yeah, this proof that we can indeed, just with one query, get the result, determine whether the function is constant or balanced. I think there's actually also another intuitive way to see why this works, which is if I consider what we're doing here, where if I look again at the circuit, so we first build an equal superposition with no phases at all. If we now apply the oracle, and if it's, for example, constantly 0, then the effect of this oracle is just none, because the effect it gives us, this minus 1 to the power f of x term, doesn't do anything, because f of x is constantly 0. So if it's constantly 0, here we just stay in the same state as before. Psi 2 would be the same as psi 1. And then we apply Hadamard Gates again, and we know that applying Hadamard Gates twice is the same as doing nothing. So we would just go back to the 0 state that we had before. And the same also holds if it's just 1. We'll just get an overall global phase of minus 1, but every single qubit will just get a minus 1 phase, so in the end, it's again the same state. So it is kind of clear that if it's constant, we will go back to the 0-bit string if one thinks a bit about the effect of that the oracle actually has. Yeah, so one thing that I still thought that my impression was when I learned about this algorithm is that, okay, now I'm still applying the oracle to all the different qubits. So I'm to the superposition of all 2 to the n. Like I'm preparing a superposition here of 2 to the n different bit strings, and then I'm applying the oracle to all of them. So why does it not count as applying the oracle 2 to the n times? But well, the reason is that for the oracle function, it's just it can be some physical implementation that really doesn't care whether you put in a superposition or just a single bit string. It's just depending on the implementation, the oracle could just be some laser pulses that you apply. So this is just one time step. You apply, for example, some laser pulses. And it really does not matter for that whether or not you're in a superposition. The oracle doesn't need to know. It just applies that no matter what state you're in. And that's the nice thing about quantum mechanics. You can be in the superposition state, and physical devices won't care in the sense as that you don't need to go through all the different, it's not 2 to the n different steps, but just one step. Yeah, so we can see that this was, I believe this was the first quantum algorithm that got famous for showing that there is a quantum advantage, that with quantum systems we can do things faster and have some advantage compared to classical systems. So I hope that was not too math intense, and I'm looking forward to teach about Rover in the next session.